So last time we were working with this system of equations, I believe we had dx dt equal to x and dy dt equal to 4x minus y. And we did the whole, and we also had x of 0 equal to 2 and y of 0 equal to 10. And so we did the whole thing, right? We found the eigenvalues. The eigenvalues were 1 and -1. We found the corresponding eigenvectors. The eigenvectors were, let's see, 1, 2, and what was the other one? I think like 2, 3 or something. The other one was 0, 1, not 2, 3. And then we use this to solve the system of equations. So I want to point out, if you're looking at your homework assignment, there is, oh, where is that question? I guess it's not super important. Anyway, right. So, but just to point a few things out, to kind of clarify what's going on with your homework, right? Like when you're writing the system of equations, we're really writing, the vector x prime of t is equal to the matrix 1, 0, 4, -1 times the vector x of t, y of t. Right, and that's equal to this. This is just vector notation for dx dt, dy dt as a vector. But what I'm really trying to say is we did this, and then we wrote down the solution, right? And the solution, and you're going to want to commit this to memory, right? The solution is that x of t, y of t. And I'm probably going to start using x1 and x2 because it's a little bit nicer. Right? This we call this the vector x of t. This is equal to, so here's the thing you want to memorize, c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. Where lambda 1 and v1 are the first eigenvalue and eigenvector, lambda 2 and v2 are the second eigenvalue and eigenvector. All right. And then we solved this. And I don't remember if we actually, I think we finished solving it. So the way you solve this, right, is you plug in what you get at time equals 0. So at time equals 0, we have x is 2, y is 10. And that's equal to c1 e to the lambda 1t, e to the 0 is just 1. So it's c1 times v1 plus c2 times 1 times v2. Oh yeah, we definitely did this one because I talked about how it's easy to solve this one, because if you have a 0 here, 2 equals c1 times 1 plus c2 times 0. So that means c1 equals 2. And 10 equals c1 times 2 plus c2 times 1. The c1 is 2, so 10 equals 4 plus c2. So c2 has to equal 6. So our actual solution to this system of equations is that x of t, I'll write down the other side here. Our solution to the system is that x of t, which is x of t, y of t, is equal to c1, which is 2. So 2 times e to the lambda 1, which was positive 1, times v1, which was, I forgot, 1, 2. Right? c1 e to the lambda 1t times v1 plus c2 e to the lambda 2 times t times v2. That is how you write your solution. Now, there's a couple, or at least one question in the homework where they ask you specifically, like, what's x of t or x1 of t, what's x2 of t? I think, like, I'm looking at question 8 and 9 in your homework, where instead of giving the answer like this, you specifically want to say, well, x of t here would just be what's in the first column. In fact, you could, if you wanted to, you can multiply this out. It's kind of weird, but you could say this is, right, it's 2e to the t times 1, so it's going to be 1 times e to the t, and then 2e to the t times 2, so 4 times e to the t, plus 6e to the negative t times 0, 6e to the negative t times 1. So you can write this as one vector, right? It's literally e to the t and 4e to the t plus 6e to the negative t. But if I want just x of t, it's what's in the first row. So here, and somehow I missed a 2 there. Sorry, that should be a 2 times e to the t times 1. 2e to the t. So here, x of t would just be the first thing, which is 2e to the t, and y of t would be the second thing, which is 4e to the t plus 6e to the negative t. Okay. You guys cool with that? Hope so. So now what I want to say is we can also talk about what the phase plane for this looks like. And there's one question I think in your homework where you're asked to like match up like systems of differential equations with their corresponding phase planes. And there's a couple ways to go about doing this. So I'm going to kind of show you the easy kind of way to do it first, but then I'm going to talk about the less easy way, but that's the thing that we're going to be doing more of as we go along here. So let me grab my examples again. Yeah, so we've got our solution there. It looks really good. And yes, as t goes to infinity, you could talk about how both of these, both x and y, both get very, very large. So let's talk about graphing the phase plane. And the thing about this is, it's not easy to do, at least not if you're going to try to graph with a bunch of points. So if I was trying to match this to say something that was given to me, here's what I would do. Well, actually, before that, I want to talk about the equilibrium. So when you're finding an equilibrium, I want to make this very exceptionally clear. When you're finding an equilibrium, you're talking about the rate of change being 0, right? Things aren't changing if we're in equilibrium, which means the derivative should equal 0, and the derivative should equal 0. And something worth knowing is that for linear systems of differential equations, right? So where we have something like dx dt is ax plus by, and dy dt equals cx plus dy, right? Where we just have coefficients of x and y and nothing else. The origin 0, 0 is always going to be in equilibrium. It might be the only equilibrium. It might not be. I think it might be the only one, unless these are the same and then you have like lots of equilibrium. But x equal to 0, y equal to 0 is an equilibrium. Meaning, if you're on that point, you don't actually move anywhere else. Just like he was talking about in class today, where like the origin of that example was an equilibrium. So if you're there, you don't move. But if you're like to the right or to the left, you move. You're moving in towards it because it was a stable one. Yes. So here's how we could try to start graphing the direction field here. This is where things get to be kind of a pain in the butt. I'm going to do just a few because this gets old fast. So typically, if I'm trying to see what a direction field might look like, I use the points 1, 1, negative 1, 1, negative 1, negative 1, and 1, negative 1. So and we can make a little table if you want. X, y, dx dt, dy dt. So if x is 1 and y is 1, then dx dt is going to be 1, and dy dt is going to be 4 minus 1, which is 3. So at the point 1, 1, I'm going 1 over and 3 up. Now I'm not going to go all the way 1 over and 3 up. I'm not going to draw that. That would be silly. I'm just going to draw a small vector in that direction. And actually, I'm not going to draw it emanating from the point. I'm going to draw it so like half of it starts before the point and half of it starts after the point. So I'm going in this direction, but I want it to be like maybe like that. So that's kind of the idea. And then at negative 1, 1, we're going to get dx dt being negative 1 and dy dt being negative 4 minus 1, which is negative 5. So I'm going left 1 and down 5. So left 1 and down, right? So it's super steep. It's going like that. And then at the point -1, -1, dy dt is going to be -4 + 1, which is -3. So from here, I'm going left 1 and down 3. So not quite as steeply down. So maybe more like that. And then at the point 1, -1, x is 1, y is -1, x is 1, y is 5. So it's going to be going more steeply up. So, oh, sorry. Of course, yeah. So for anyone that's ever having internet issues at all, if you can't watch class right at the moment, that's perfectly fine. You're welcome to watch it later. Just send me an email after you watch it, letting me know, and I will record your attendance. So yes, whoever has messaged me is welcome to watch later if that is what you need to do. So as you might have noticed, this is a tedious task, right? We don't want to, like, I've already done 4 points and I haven't gotten much, and we can kind of do some more, but it's not the nicest process. That said, I do think this process will be perfectly sufficient for completing problem 6 in your homework assignment. So if you want to, for any of those, just plot a few points, you can kind of see, oh, that's going to look like such and such graph. But let me we should really talk more about where we're going with this. And where we're going with this is we actually want to draw or have a better kind of way of drawing the system of equations. So there are 2 things to be super aware of. And they are the eigenlines, which are just the lines that the eigenvector would live on, and the nullclines, which are the lines where either derivative is equal to 0. So are we good here? Yeah, I think we can even use what I've got already. And maybe we'll keep these on here. So the eigenlines, remember, so back in 17b, Karana talked about the lines that the eigenvector lived on, and it's why she actually did, that's why she was doing that, because we talk about them now. So I erased, here's my eigenvectors. And if you remember, we got the first eigenvector, v1, right? We got that by saying y was equal to 2x. I know I didn't show the work today, but that's how you're getting x is 1 and y is 2. X is 1, y is 2. But this line, that's the eigenline. So let's draw, I'm going to draw my, I guess I'll draw my eigenlines in black. So one of the eigenlines is y equals 2x. So over 1 up 2. And how do I want to draw these? Yeah, I guess I want to draw these like this. So my eigenlines look like this. Sure. And now here's the thing that you want to know. If this eigenline, right, eigenline for v1, the eigenvalue was 1, which is positive. If your eigenvalue is positive, it means that your arrows point away from the origin. So my arrows are going to point this way. In fact, if I was drawing the direction or the phase plane, I would literally, I'd have an arrow, in fact, that's what I was going to do. So I was going to draw this more like this. So right over here at the point, 1, 2, there would be an arrow going exactly in that direction. So basically, on the eigenline, the phase plane arrows actually go in the direction of the eigenline. And I feel like my picture's kind of falling apart here. So I'm trying to make this look a little bit nicer. Sorry, this is the challenging part, is trying to make it look somewhat decent. Let's get 1, 2, 3, 4. Okay. So, right, at the point 1, 2, the vector would be going in the direction of 1, 2. At the point 2, 4, the vector would be going in the direction, right? These are all in the direction of the line y equals 2x. But usually we just draw it as a line. And we're like, okay, the arrows point outward. Okay, let's draw the other eigenline. The other eigenline was with the eigenvector v2 equal to 0, 1. Okay, we got to be careful here. So we had x equal to 0. So basically we have x equal to, yeah. So the equation we had was x equal to 0, right? That's how we got this eigenvector, which is x is 0 and then y can be anything. So that's going to be the vertical line, x is 0. Great. And since the eigenvalue for this was negative, the arrows are going to point in towards the origin. Okay. And then we can also talk about the Nullclines. So the Nullclines, I think they're also called isoclines. I feel like isocline might not be right. Definitely Nullclines. The Nullclines are where each thing is equal to 0. So, oh, that's, I feel like I might be making a small, no, I don't think that's wrong. Sorry, 1 sec. I'm just, no, that's right, okay. No, yeah, that's perfectly fine. Yeah, sorry, I'm just, yeah. Okay, so the thing that's kind of weird here is one of my eigenlines is also one of my Nullclines. That happens sometimes. So the Nullclines are what we get when we set either one equal to 0. So where'd my blue pen go? So we can either set x equal to 0, okay. So when we set x equal to 0, right, that's again this vertical line. Now here's what you want to know about a Nullcline. When I'm setting x equal to 0, I'm also setting the first derivative dx dt equal to 0. So here's what we're saying. Along the line x equal to 0, which is this vertical line, dx dt, the horizontal change, is 0, meaning all my arrows should be perfectly vertical along that line. And they are. Let's look at the other. I knew I made this steeper than I wanted to make it. So, oh well, my picture's going to look a little bit funky. For the other isocline, we're going to set 4x minus y equal to 0. So we're going to get y equal to 4x. But that's, so this line, y equal to 4x, which you know is pretty steep. It looks like this. Sorry, my lines aren't perfect. So here's the thing. On this line, dy dt is equal to 0. That means the change in the y direction is 0, which means all of the lines have to be horizontal. So like at a point here, we have a horizontal arrow. Point here, we have a horizontal arrow, horizontal arrow, horizontal arrow. And the same would be true over here. We'd have horizontal arrows. I'm not actually sure if they're pointing left or right, but we could check, right? So up here, I mean, arrows should be pointing, let's see, if I have the point like, 1, 3, if x, well, if x is 1, our dx dt is definitely, oh, sorry, not the point 1, 3, we have to go on line. So at the point 1, 4, if x is 1, it's positive. If x is 1, y is 4, this is 0. We have the point -1, -4, dx dt will be -1, so we'll be pointing to the left. These are all pointing to the left. So you might not believe me yet, but the point of this is that it allows us to kind of see what the phase plane looks like. So here's what's going to be happening. Anywhere, so these eigenlines, the lines in black, are kind of, what's the word? There's some words here that, let's see, so I had written some, just 1 sec. Oh, there were some great words. Yeah. So the eigenlines represent the strongest lines of attraction or repulsion to the equilibrium. Vectors on eigenlines associated with negative eigenvalues point inward, like we have, and vectors on eigenlines with positive eigenvalues point outward. So the ones with negative eigenvalues are attracted to the origin, to the equilibrium, and the ones with positive eigenvalues are repelled. And so then if we start like somewhere out here, we're going to kind of move in this, like in this kind of direction like that. Right? So that we're moving we're moving towards the equilibrium, but then this other one's kind of repelling us away from it. Same kind of deal over here. We're moving this way. And then in here, we would kind of move in, but then away. Okay, so let me kind of show you on P-plane how this actually looks. Up here, just grab it. I wonder if I can do it that way. I wonder how I can share my screen here. I can. Can you guys see that? No, now I'm sure you can. But I didn't share the whole thing. Sorry, one sec. Let me just do this instead. Sorry. Let me just share my screen now. Okay. Share. Cool. So here's P-plane, and I have some different equations in there. Let me put the right equations in. So the equation again was dx dt equals x, and dy dt equals 4x minus y. Let's graph it. Let's make our window not quite as big. So here's the origin. And then you can kind of, I mean, if you look at what we've got here, right, you can see, oh yeah, my arrows, if we start down here, we go this way, and we kind of move off that way. So what's cool about this is you can actually click on P-plane anywhere. So let's say we had initial conditions, which I picked were too big. I mean, I guess we can make this bigger, but let's say this, so yeah, fine, let's go bigger. Let's go, sure. Okay, so the initial conditions that we were given, I believe for this problem were, I think there were 2 and 10. Does that sound right? Sounds right. So if we go over to x equal to, okay, 2 is probably like about right there, and 10 is up here. It tells us what's going to happen, right? If you move, so you're going to move in this direction like that. Whereas if we started somewhere like, I don't know, over at 0, 5, we're going to move that way, like this. So if we're up in here, we're going to move like that. If we're over here, we're going to move like that. If we're over here, we're going to move like that. If we're down here, we're going to, do something crazy like that. So it's really a powerful tool. I think it's worth using. But the point I really am trying to make here is that we can get a good idea of what's going on by drawing the Nullclines and the Eigenlines. And you don't actually, I should really say, the Nullclines are the more important thing. The Eigenlines, yes, also important, but the Nullclines are really kind of what help us see what's happening. Yeah. Okay, so let me stop sharing. So negative eigenvalues are attracted to the origin, positive eigenvalues are repelled. Excellent, Max. Yes, exactly. And so what's going to happen, what we're going to see very soon, probably next week, is that if both your eigenvalues are negative, the whole thing is going inward towards the origin. And you have what's called a sink, which is a stable node. If both the eigenvalues are positive, everything's going to shoot outwards. And you have what's called a source, or an unstable node. And if you have this sort of situation where one is positive and one is negative, you have a saddle where one eigenline is pushing, or where one eigenline is pushing you in towards the towards the equilibrium, and the other eigenline is pushing you out, or the other, I'm sorry, I'm just using the other isocline. So one isocline is pushing you in towards the stable, and one isocline is pushing you out. No, I should be saying Eigenlines, yeah. It can take practice, as you might have noticed. And like it can take practice to be really confident about what you're saying about the lines. Let me see one more thing here. Yeah. Yeah. Okay. Yeah. Sorry, this always takes a minute for me to wrap my brain around. I'm like, okay, yeah, this makes sense. Yeah. So it's definitely, yeah, it's about, yeah, it's about what the eigenlines are doing. Sorry, I know I went back and forth on that one. So yeah, so right, because the eigenlines are what the eigenvalues are attached to. So right, we have one eigenline pushing us in, we have one eigenline pushing us out. That's giving us a saddle, which is what we have in this p-plane plot over here, right? This, so right, if you look at this, I'm going to show you guys this again just to show you a little bit more. Right, if we plot some more points on this, or if we draw some more lines, you guys can kind of see, oh yeah, this is looking very saddle-y, right? You've got kind of a, it's not really right, but you've got kind of a maximum thing one way and a minimum thing the other way. So you, right, if you were thinking of this as like as contours, right, and these ones are low, these are the low ones and these are the high ones, for example, you've definitely got what's a saddle. So yeah. And then we'll see for imaginary eigenvalues, for complex eigenvalues, you get spirals. So cool. It's actually really kind of cool, but it does take practice to wrap your brain around. So let's look at some more examples. So let's look at this next example. And again, I do think it's worth our time to practice finding the solution of these systems of linear equations. But we're going to talk about how you can see things kind of very early on. So let's look at this next one. So here's our general equation. Dx dt is negative 2x plus y. And dy dt is 2x minus 3y. And if you think about this, here y is having a positive effect on x, right? Dx, the change in x, if y is positive, the change in x will be more positive or is bigger, right? Here, x is having a positive effect on y, right? The bigger x is, the bigger the change in y is going to be. So let's find all the things. So we're going to find the general solution. Which is the, and I'm going to use, instead of using x and y, let's use x1 and x2. So dx1 dt is 2x minus 2x1 plus x2, and dx2 dt is 2x1 minus 3x2. And our general solution is going to be x1 of t, x2 of t equals c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. Have you memorized that yet? You should. Okay. So let's find the eigenvalues. I'm gonna do the eigenvalues the new way, where we say, okay, the trace of this matrix. So the trace is just the sum. Oh, I should write down the matrix, I suppose. The matrix is just the matrix of coefficients. Our matrix A is -2, 1, 2, -3. And the trace of that matrix is just what you get when you add up the diagonal elements, right? The diagonal elements is everything starting from the upper left to the lower right. So the trace is going to be -2 plus -3, which is -5. The determinant is going to be -2 times -3 minus 1 times 2, which is going to be 6 minus 2, which is 4. The eigenvalues is going to be the trace plus or minus the square root of the trace squared minus 4 delta all over 2. Again, I'll mention this is probably maybe slightly overkill for these ones that turn out to be nice. But for the ones that turn out to be not nice, it's actually kind of the easiest way. And when you start the problem, you don't know if it's going to be nice or not. So this is probably what you should do. I know it's a new way of doing it, but it's worth your time to try and do it this way. So that's going to be -5 plus or minus the square root of -5 squared minus 4 times 4 is 16 all over 2. So that's going to be -5 plus or minus 3 all over 2. -5 plus 3 is -2 over 2, so -1. Or -5 minus 3 is -8 over 2, so -4. So let me tell you something. Seeing that these are both negative, we know both of our eigenlines are going to point inward towards the equilibrium, towards the origin, which is the equilibrium. So we already can classify what kind of phase plane we have just by knowing something about the eigenvalues, which is kind of great. We're still going to draw things, but it's good to know that. So let's find the system. Oh, we have to find the eigenvectors. So let's see. I have my system here. A is -2, 1, 2, -3. I said it, forgot it. -2, 1, 2, -3. -2, 1, 2, -3. -2, 1, 2, -3. Is that right? Let's check. It is. Okay, and then our eigenvalues are -1, -4. Doesn't matter which one you call which, just be consistent. So lambda1 is going to be -1, lambda2 is going to be -4. So for lambda1, we're going to have -2, 1, 2, -3 times, I guess here's where I'd probably use x and y. You can use x1 and x2, but we already kind of used them. Equals -1 times xy. I should take a screenshot of the attendance so I can enter it later. Gosh, there's so many of you, which is great. I'm glad there's so many of you. Thank you for coming. Although Grant has like 70 people in his class, which is kind of bonkers. Anyway, so we've got -2x plus 1y equals -x. So then we'll solve for y, and we'll get y equal to x. There's our eigenline. And our eigenvector is 1, 1. And then for lambda2 equal to -4, so this was this, and then this is going to be right down here. We have -2, 1, -2, 3 times xy equal to -4 times xy. And we'll get, let's see, -2x plus y equals -4x. So we're going to get y equal to -4x plus 2x is -2x. So that's the other eigenline. And the eigenvector is going to be x is 1, y is -2. Great. So finding the solutions, the general solution of the system is going to be that x1 of t, y1 of t equals c1 e to the lambda1 times v1 plus c2 e to the lambda2 times t times v2. And if we're not given any initial condition, this is just our general solution. Okay. So now, what I really want to do is sketch the. Let's talk about why this is a sink. So in the previous one, I know I said that as you let time go on and on and on, you get things going to infinity, right? Our previous solution, I don't remember exactly what it was, but it was something like 2e to the t and 4e to the t plus 6e to the -t. I think that's what it was. And you let t go to infinity, that goes to infinity, that goes to infinity, that goes to 0. Both of them go to infinity. So both x and y were going to infinity in the previous one. But in this one, if you let t go to infinity, e to the negative t goes to 0 as t goes to infinity. And e to the negative 4t goes to 0 as t goes to infinity. So this one, as you let time go on, goes to 0, 0, which means you're shooting towards your stable equilibrium. That's the origin. So that's why everything's going to be pointing inwards, because as you let time go on, everything goes towards being 0 here. So let's sketch the phase plane. Sorry, one sec. I'm just looking at something here. Oh, I see. Okay. Oops, I just erased all the work. I meant to not erase. Oh, well, that's all right. I remember what things were. So our eigenvalues were lambda 1 equal to negative 1, and the eigenvector was, what was the eigenvector? I thought I remembered. Let me look back here. It's 1, 1. I got that. And for lambda 1 equal to negative 4, the eigenvector, sorry, for lambda 2 equal to negative 4, the eigenvector was 1, negative 2. Yeah. Okay. And then our equations, just so you guys remember what they were, but the equations were dx1 dt equal to, where'd you go? Negative 2x1 plus x2, and dx2 dt was equal to, what do we got here? Sorry, 2x1 minus 3x2. Okay. So that's what we're working with. So let's draw the eigenlines. And yeah. Right, so this, I know I erased it, but this was from, so here's the thing, you could draw like this. I know it's gonna be y equals x, or I'm gonna say the vector is 1, 1. I'm gonna go over 1 and up 1. So there's my, now I shouldn't draw that arrow. There's my eigenline for lambda 1 equal to negative 1. And the arrow should point inwards because the eigenvalue is negative. And then for the other eigenvalue, the eigenline is you go over 1 and down 2. Or you could figure out that it's y equal to negative 2x. So that's going to be that eigenline. Look like that. And again, things should be pointing inwards because the eigenvalue is negative. And then let's also draw the nullclines, because while yes, you can see that everything's pointing inwards, and not everything's pointing in like 100%. Like if you start here, you're not exactly pointing at the origin, right? You're kind of pointing. Well, I'll show you. So let's draw the eigenlines. So setting the so it's important to know that the different eigenlines kind of, it matters which one's which. So it matters that there's an x eigenline. Sorry, nullcline. Apologies. So for the nullclines, there's one for x1 and then there's one for x2. Or actually there can be multiples, but for these there's only one. And I would encourage you to draw your x1 or x nullclines in a different color than your x2 or y nullclines. It will make your life a little easier later on when we're trying to see things. So for the x1 nullcline, I'm just going to be setting this equal to 0. And for the x2 nullcline, I'm going to be setting this equal to 0. Okay. And then I'm just going to find what I get. So for the x2 nullcline, I'm solving this. I'm going to solve for x2, which is my y. Right, this is the x1 axis. This is the x2 axis. If I solve for this, I'm going to get x2 equal to 2x1. That's going to be over 1 and up 2. Okay, and the thing to remember about a nullcline is that you're saying that this thing is equal to 0, which means the derivative is equal to 0, which means the rate of change in the x1 direction is 0, which means here all my lines are straight up vertical. So that's always true about nullclines. For the x1 or x nullcline, all the arrows on it are vertical. For the x2 nullcline, all the arrows on it are horizontal. And then let's draw the other one. So for solving this one, if I solve for x2 again, I get 2x1 equal to 3x2. I get x2 equal to 2/3 x1. So I'm going to go, let's see, if x1, I'm going to go over 3 and up 2. Right? Because if x1 is 3, x2 is 2. So this one's going to look like this. And again, things are going to be pointing not inward, not inward, but horizontal. So then if I started somewhere at like, I don't know, say I started at the point, so let's say my initial conditions were x1 of 0 equals 8 and x2 of 0 equals 2. Then I would start way over here at the point, 8, 2, and I would be, I would be pointing kind of this way, right? It would kind of point me like that towards the origin. Or if I started at the point 1, 6, it would kind of point me like that. So you're not straight, like it's not a straight shot to the origin. You're still kind of along some curve. And we can, again, we can see this more nicely if we look at the p-plane. So let's get old p-plane going again here. I can't emphasize enough. I really think if you have the opportunity to, it is worth your while to download p-plane so you can see what things look like. So our system of equations was dx1 equals -2x1, which is x, plus x2, which is y. And our second equation was dx2 is 2x1, which is 2x minus 3y. Whoops, I need a minus sign there. Well, let's make it a little bit less big. So there it is. You can see, oh yeah, things are pointing inwards. But if we start at the point 8, 2, just like right about there, right? I think that's 8, 2, yeah. Look, oh yeah, we're going like that. And we start at the point 1, 6. Oh yeah, we're going like that. So what I always think is kind of fun to do, which is lame but kind of fun, is if you try and click on an eigen line specifically, it should be a straight shot to the origin. So if I was trying to land on the line like y equals x, it should point straight to the origin. So let's see, can I get y equals x? So I need to point like 2, 2. So the thing is, it's really hard to get it exactly right, because if you look down there in the lower left corner, right, it shows you the numbers. If you don't get them exactly the same, you kind of don't really get what you want. So let's try 3, 3, 4, 4. I know this is really fun watching me do this. Look, there we go, pretty good, right? It's basically just straight pointing in. So the eigen line is the line that basically, if you're on that line, you're just going to travel in the direction of that line. Whereas anywhere else, you're going to get kind of pushed towards your eigenlines, right? And my eigenline was that one, and the other eigenline was, sorry, where'd you go? This one here, over 2, down 3, right? So if we go real quick, I know we're out of time, but this is too fun. I know it's not really that fun, but it's kind of fun. Right, so here's our other eigenline, right? So basically, anywhere in here, you're getting pushed. So we're getting pushed up this way, but then this eigenline is kind of like the barrier. Whereas if we start, like say, and here's the other side of the eigenline, right? oops, it's hard to get like perfect. You can see like all these points, right? They kind of go towards the eigenline. If you start way out here, whoop, so I mean you can click all day, right? But the point is that the eigenlines are kind of like these barriers where if you start somewhere way off of it, eventually you're going to get pushed towards it and then smushed in towards there. If you have this sort of thing where the eigenvalues are both negative. On the other hand, if eigenvalues are both positive, everything will be getting pushed outward in the way. So we'll definitely talk about this more on Monday, but I think you guys are in a pretty good place. Like you should be.